The concept of time is something that we experience every day: the ticking of the clock, the passing of days, the cyclical nature of seasons. Time is so ingrained in our daily lives that it can be easy to forget how much of a mystery it truly is. While we have a practical understanding of how time operates on Earth, our understanding of time in the context of the universe's origin and eventual end is far more complex and elusive. To comprehend how time might end, we must first understand how it began and how it relates to the very structure of the universe itself. The traditional everyday understanding of time is based on the idea that time moves in a straight line, from past to present to future. This flow of time is often referred to as the arrow of time, and it seems to be a one-way journey. We experience time as a sequence of events. The past is fixed, the present is fleeting, and the future is unknown. However, this straightforward view of time becomes far more complicated when we step outside of our own experiences and look at the universe as a whole. Our modern understanding of time began with the advent of Albert Einstein's theory of relativity in the early 20th century. Prior to Einstein, time was seen as an absolute fixed quantity, the same for everyone, everywhere. However, Einstein's special theory of relativity fundamentally changed this view. In 1905, Einstein proposed that time is not absolute but relative. It depends on the observer's frame of reference. The famous equation E=mc2, which relates energy and mass, was derived from his work, but it was his work on the nature of space and time that had the most profound implications for our understanding of the universe. Einstein's theory of special relativity showed that time could stretch and contract, depending on how fast an object is moving relative to the observer. This phenomenon is known as time dilation. For example, an astronaut traveling at near-light speeds would experience time much more slowly than someone on Earth. If the astronaut were to return after a long journey through space, they would find that less time had passed for them than for those left behind on Earth. This strange effect has been confirmed through various experiments, such as measuring the difference in time between atomic clocks placed at different altitudes. Einstein's general theory of relativity, published in 1915, extended these ideas to include gravity, showing that time is also affected by the curvature of space-time. According to general relativity, massive objects like stars and planets warp the fabric of space-time, causing time to slow down in their gravitational fields. The closer you are to a massive object, the more time slows down. For example, time runs slightly slower at sea level compared to the top of a mountain due to the Earth's gravitational pull. This phenomenon, known as gravitational time dilation, has been measured with great precision using highly accurate atomic clocks. The fact that time can slow down depending on gravity or speed shows that time is not a simple, unchanging backdrop against which events unfold. It is an integral part of the universe that is shaped by mass, energy, and velocity. But while Einstein's theories revolutionized our understanding of time, they also presented a new puzzle. How did time itself begin? If time is intertwined with the fabric of space, then how did it come into existence? The answer to this question lies at the very origin of the universe, in the event known as the Big Bang. The Big Bang theory is the prevailing scientific explanation for the origin of the universe. According to this theory, the universe began around 13.8 billion years ago as an infinitely hot, dense point known as a singularity. At this moment, space, time, and all of the matter and energy in the universe were compressed into an incredibly small volume. It was at this singularity that both space and time came into existence. The Big Bang is not an explosion in space. Rather, it is the expansion of space itself. As the universe expanded, it cooled, allowing the formation of matter and the development of the galaxies, stars, and planets that make up the universe we observe today. The Big Bang theory is supported by a wide range of evidence. One of the most compelling pieces of evidence is the cosmic microwave background radiation, CMB, which is a faint glow of radiation that fills the entire universe. This radiation is considered the afterglow of the Big Bang, a remnant from the early universe when it was hot and dense. The CMB was first detected in 1965 by Arno Penzias and Robert Wilson, and it has since been studied extensively by astronomers. The CMB provides a snapshot of the universe just 380,000 years after the Big Bang, and its uniformity and specific patterns offer strong evidence for the theory. Another key piece of evidence supporting the Big Bang theory is the observation that the universe is expanding. In 1929, astronomer Edwin Hubble discovered that galaxies are moving away from us in all directions. This observation, known as Hubble's law, showed that the universe is not static, but expanding over time. If the universe is expanding, it suggests that it must have been much smaller and denser in the past, providing further support for the idea of a Big Bang origin. However, the question of time itself remains mysterious. The Big Bang marked the beginning of time as we know it, but what happened before the Big Bang? This is a question that has puzzled cosmologists for decades. According to general relativity, time and space are part of the same fabric, space-time, and the Big Bang marked the moment when both space and time came into existence. If time itself began at the Big Bang, then it doesn't make sense to ask what happened before it, as there was no before in the conventional sense. Time itself is thought to have emerged along with space and matter, and any notion of before the Big Bang is beyond the reach of current scientific understanding. One intriguing possibility is that the Big Bang was not the beginning of time itself, but rather a transition point in a much larger cycle. Some cosmological models propose the idea of a cyclic universe, where the universe undergoes an infinite series of expansions and contractions, each one starting with a Big Bang and ending in a big crunch. In this scenario, time is not a one-way journey, but a series of cycles that repeat eternally. This idea is still speculative, and there's currently no direct evidence to support it. But it offers a fascinating alternative to the conventional view of the Big Bang as the absolute beginning of time. As we consider the nature of time and its relationship to the universe, we also must confront the fact that time is an emergent property of the universe. While we experience time as a linear, measurable progression, our perception of time is a construct that arises from the laws of physics. In the realm of quantum mechanics, time becomes even more elusive. Quantum mechanics describes the behavior of particles at the smallest scales, and at these scales, time is not always well defined. Some quantum theories suggest that time may not exist at the most fundamental level, or that it could behave in ways that defy our everyday understanding. The interplay between time and space becomes even more mysterious when we delve into the realm of black holes. Black holes are regions of space where the gravitational pull is so strong that nothing, not even light, can escape. At the heart of a black hole lies the singularity, a point of infinite density where space-time curves infinitely, and the laws of physics as we know them break down. In these extreme environments, time behaves in strange and counterintuitive ways. According to general relativity, time slows down as an object approaches the event horizon of a black hole, the boundary beyond which nothing can escape. At the event horizon, time effectively comes to a standstill relative to an outside observer. The study of black holes, along with the continued exploration of quantum mechanics and cosmology, is likely to provide new insights into the nature of time. In recent years, scientists have proposed theories such as loop quantum gravity, which attempts to reconcile the principles of quantum mechanics with general relativity, and string theory, which proposes that time might have additional dimensions that we cannot perceive. These theories, while still in their infancy, offer promising avenues for understanding the deeper structure of space-time and how time itself might work on the most fundamental level. In the quest to understand time, we are confronted with profound questions that go beyond the boundaries of science. Time is not just a measure of change, it is a concept that shapes our perception of reality and our place in the universe. As we explore the origins of the universe, the nature of space and time, and the fate of the cosmos, we realize that the answers we seek may be far more complex than we ever imagined. The story of time is not just about the past and the future. It is about the present, the moment we are living in now. Time may be a construct of the universe, but it is also the medium through which we experience existence. The search to understand time is a journey that takes us to the very edges of knowledge and beyond. As we continue to study the cosmos and unlock its deepest secrets, we will come closer to understanding the true nature of time and the role it plays in shaping the universe. The flow of time, the way it moves from the past to the present and then into the future, is something we experience every day. We all have an innate understanding that time moves in one direction, forward. Yet, despite our everyday experience of time, the fundamental question of why time flows in only one direction has long puzzled scientists and philosophers alike. This concept, known as the arrow of time, is one of the most profound mysteries in the universe. To understand why time flows in a particular direction, we need to delve into the concept of entropy, a key concept in the second law of thermodynamics. The second law states that in any isolated system, the total amount of entropy, a measure of disorder or randomness, always increases over time. This idea suggests that the universe, as a whole, is constantly moving towards a state of higher disorder. But what does this mean for the direction of time? The increase of entropy is what gives time its direction. In a closed system such as the entire universe, entropy is constantly increasing, and the universe is moving towards a state of maximum entropy, also known as thermodynamic equilibrium. This state of maximum entropy is a condition where no useful energy remains, and everything is evenly distributed and in a state of perfect disorder. The idea is that time progresses in the direction in which entropy increases, from a state of lower entropy, order, to higher entropy, disorder. This is what gives time its arrow. It moves in the direction of increasing chaos or entropy. While this idea might seem simple, it has profound implications. Entropy not only gives time its direction, but it also tells us that the universe started in a highly ordered state and is gradually moving toward a state of maximum disorder. This is often referred to as the heat death of the universe, a state where all stars have burned out, galaxies have drifted apart, and the universe has reached a state of complete uniformity and coldness, with no thermodynamic processes left to drive any kind of activity. In this scenario, time would continue, but there would be no events or changes, no motion, no life, and no energy. It would be a universe frozen in time, unable to undergo any further processes. One of the most perplexing aspects of the arrow of time is that while entropy always increases, the fundamental laws of physics themselves do not seem to prefer any particular direction. In fact, most of the laws of physics, such as those governing motion, gravity, and electromagnetism, are time-symmetric, meaning that they work the same way forwards in time as they do backwards. For example, if you were to reverse the motion of a ball rolling down a hill, the ball would still obey the laws of physics as it rolled uphill. So, why is it that in our everyday experience, time only moves in one direction? The key to this question lies in the initial conditions of the universe. At the time of the Big Bang, the universe began in a state of extremely low entropy. It was highly ordered and concentrated in a very small, dense point. From this state, the universe began to expand, and as it did, entropy increased and the universe became more and more disordered. This initial low entropy condition is what gives time its direction. The arrow of time points from the low entropy state of the Big Bang towards the high entropy state of the heat death of the universe. In essence, time flows in one direction because the universe started in an ordered state and has been moving towards disorder ever since. While entropy is the key to understanding the direction of time, there are other factors that influence how we perceive the passage of time. One of these factors is cosmological expansion, the idea that the universe itself is expanding over time. As the universe expands, galaxies are moving farther apart, and the fabric of space-time is stretching. This expansion has a profound effect on the passage of time. For example, the expansion of the universe causes the light from distant galaxies to stretch, or redshift, as it travels across space. This stretching of light is one of the key pieces of evidence that the universe is expanding, and it is a direct consequence of the flow of time. Interestingly, the expansion of the universe also has implications for how we experience the passage of time. As galaxies move farther apart, the distance between us and other objects in the universe increases. This means that light from distant galaxies takes longer to reach us, and as a result, we see these galaxies as they were in the past. The farther away a galaxy is, the further back in time we are observing it. In this sense, the flow of time in the universe is not uniform. We are constantly looking into the past when we observe distant objects, and this gives us a sense of time as an ongoing process, where the past is always just out of reach. Another important aspect of the arrow of time is psychological time, the way we experience time on a personal level. Our minds are attuned to the passage of time, and we experience time as a sequence of events. We remember the past, experience the present, and anticipate the future. But why is it that we perceive time this way? Why do we have a clear sense of the flow of time when the laws of physics do not inherently favor a particular direction? One possible explanation lies in the structure of our brains and our perception of cause and effect. We are wired to see events as having causes and consequences. The experience of time is closely tied to our understanding of the world and our place within it. We measure time through events that we experience: the ticking of a clock, the changing of the seasons, the passing of our lives. In this sense, time is a subjective experience that is deeply embedded in our consciousness and our understanding of the world around us. We see time as flowing in one direction because our minds are structured to perceive it that way. But while we experience time as flowing forward, the very nature of time itself may be more fluid than we realize. In the realm of quantum mechanics, time behaves in ways that defy our everyday understanding. At the quantum level, particles exist in a superposition of states, and the concept of time becomes blurred. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that all possible outcomes of quantum events occur simultaneously in parallel universes. This raises the question: if time is not an absolute, unchanging flow, what does it mean for the direction of time in the quantum realm? Could time itself be more flexible than we think? As we move from the macroscopic scale of everyday experience to the microscopic scale of quantum mechanics, the traditional arrow of time seems less certain. In the quantum world, time appears to be intertwined with space, energy, and matter in ways that we don't yet fully understand. The very notion of time might not be as simple as a linear progression, but rather a dynamic, interdependent aspect of the universe that changes depending on the conditions under which it is measured. One of the most intriguing aspects of the arrow of time is its connection to the future of the universe. As we look forward, it becomes clear that time itself is closely linked to the expansion of the cosmos. The universe is not only expanding in space, but also evolving over time. The future of the universe is tied to the increasing entropy of the cosmos, and eventually, the universe will reach a state where time as we know it will cease to exist in any meaningful way. Theories about the future of the universe, such as the Big Freeze, the Big Crunch, or the Big Rip, all depend on the continued flow of time. Whether the universe continues to expand and cool, collapses in on itself, or tears apart, the fate of the universe will be determined by the behavior of time, entropy, and the forces that govern the cosmos. Time, in this sense, is not just an abstract concept, but a driving force in the ultimate destiny of everything that exists. The arrow of time, then, is a key to understanding the past, present, and future of the universe. It gives us a framework for thinking about the universe's beginning and its eventual end. But even as we ponder the ultimate fate of the cosmos, the true nature of time remains elusive. Time flows in one direction because of entropy, but the deeper nature of time itself, particularly at the quantum level, is still a mystery. As we continue to explore the universe, both on the large scale of galaxies and on the small scale of quantum particles, we will undoubtedly uncover new insights into the nature of time and its role in the cosmic story. The future of cosmic discovery is likely to bring even more revelations about time. As we develop new technologies and refine our understanding of space-time, we may unlock secrets that will transform our perception of the flow of time and its place in the universe. Whether we discover new aspects of time in the quantum world or learn more about the ultimate fate of the universe, the search for answers will continue to challenge our understanding of the cosmos. The concept of the Big Freeze, also known as heat death, is one of the most widely accepted theories regarding the eventual end of the universe. It is a chilling thought, a future where the universe continues to expand indefinitely, growing colder and darker with each passing moment, eventually reaching a state where life and activity are impossible. In this scenario, the universe, despite its vastness, becomes an empty frozen void where no thermodynamic processes can take place, and all matter is in a state of maximum entropy. At the heart of the Big Freeze theory lies the idea that the universe's expansion will continue to accelerate, driven by the mysterious force known as dark energy. For years, scientists had assumed that the expansion of the universe would eventually slow down and reverse under the influence of gravity, leading to a dramatic collapse, the Big Crunch. However, as we discussed earlier, in 1998, astronomers discovered that the universe's expansion was not slowing down, but actually speeding up. This acceleration, attributed to dark energy, fundamentally altered our understanding of the universe's future. If the acceleration of expansion continues indefinitely, the universe will eventually reach a state where all galaxies, stars, and other cosmic structures are too far apart for any interaction or meaningful process to occur. This scenario, known as the Big Freeze, suggests that the universe will continue to expand at an ever-increasing rate until it becomes cold, dark, and desolate. The once vibrant galaxies will drift farther and farther apart, and the stars that power them will burn out, leaving behind nothing but remnants of dead stars and cold, dark voids. One of the key elements of the Big Freeze scenario is the increase in entropy over time. As we discussed in earlier chapters, entropy is a measure of disorder or randomness in a system, and according to the second law of thermodynamics, the total entropy of the universe always increases. In a closed system, such as the universe, this means that the universe is constantly moving toward a state of maximum disorder where no usable energy remains and no processes can take place. This increase in entropy leads to the eventual end of the stars and galaxies that make up the visible universe. Stars burn their fuel in nuclear fusion reactions, converting hydrogen into heavier elements like helium. This process releases enormous amounts of energy, which powers the stars and keeps them hot. However, eventually, stars exhaust their nuclear fuel and begin to die. Smaller stars, like our Sun, will eventually expand into red giants, shedding their outer layers and leaving behind a dense core known as a white dwarf. Over billions of years, the white dwarf will gradually cool, and the star will no longer emit light or heat. Larger stars will end their lives in supernova explosions, scattering heavy elements into space and leaving behind black holes or neutron stars, objects that are incredibly dense and cold. But no matter how a star dies, the result is the same. The universe becomes colder and less hospitable to life. As stars burn out, the galaxies themselves will grow increasingly dark, with only the faint remnants of dead stars and black holes remaining. The expansion of the universe means that galaxies will move farther away from one another, and the light from distant galaxies will become redshifted beyond detection. The once dynamic, star-filled universe will fade into a quiet, dark place. One of the most unsettling aspects of the Big Freeze theory is that it suggests the ultimate death of everything. If the universe continues to expand, it will eventually reach a point where the conditions for life, or any meaningful activity, are impossible. No stars will be left to provide energy, no galaxies will be close enough to interact with one another, and no processes will occur to bring new energy into the system. The universe will enter a state of maximum entropy, where everything is evenly distributed and no significant change is possible. As the universe continues to expand, the available energy for stars to form and for life to exist will become increasingly scarce, Over vast timescales, the remnants of stars and galaxies will drift further apart, and any remaining sources of energy, such as black holes, will eventually evaporate, according to a process known as Hawking radiation. Proposed by physicist Stephen Hawking in the 1970s, Hawking radiation suggests that black holes are not truly black, but instead emit radiation due to quantum effects near their event horizons. Over incredibly long periods of time, this radiation will cause black holes to slowly lose mass and energy until they eventually vanish completely, leaving behind nothing but a cold, empty universe. At this point, the universe will have reached what is known as the heat death, a state of maximum entropy where everything is evenly distributed and no thermodynamic processes can occur. There will be no stars, no planets, no life, and no energy. The universe will be in a state of perfect stasis, unable to evolve or change in any meaningful way. This is the ultimate end of time as we understand it. Time may continue to tick forward, but with no events, no life, and no processes to mark its passage, the universe will be effectively dead. The Big Freeze scenario is supported by the current understanding of the universe's expansion and the role of dark energy. As the universe continues to expand, the rate of expansion accelerates due to the influence of dark energy, which makes up around 68% of the universe's total energy content. Dark energy is thought to have a repulsive effect on space-time, causing the universe to expand at an ever-increasing rate. This accelerating expansion means that galaxies will move farther apart, stars will burn out, and the universe will become increasingly empty and dark. However, while the Big Freeze is a plausible outcome based on our current understanding of cosmology, it is important to note that the future of the universe remains uncertain. The exact nature of dark energy is still a mystery, and our understanding of the forces that govern the universe is incomplete. Some theories suggest that dark energy could change over time, or that other factors could influence the future evolution of the cosmos. For example, some models of cosmology propose that the universe could eventually undergo a phase transition where its fundamental properties change, leading to a new phase of cosmic evolution. Another possibility is that the universe could experience a big rip, in which the accelerating expansion of the universe becomes so extreme that it tears apart galaxies, stars, and even atoms themselves. While this idea is speculative, it highlights the potential for the universe to end in a dramatic, catastrophic event rather than a gradual cooling process. The idea of the Big Rip suggests that the ultimate fate of the universe may depend on the behavior of dark energy and its impact on space-time. Despite these uncertainties, the Big Freeze remains the most widely accepted theory for the long-term fate of the universe. As time goes on and stars burn out, the universe will become a cold, dark, and empty place with no possibility for life or activity. This chilling vision of the future is a reminder of the inevitable nature of time and the universe's constant march toward entropy and disorder. Yet, while the Big Freeze might signal the end of the universe as we know it, it is also a reflection of the awe-inspiring scale of cosmic time, a time scale that stretches far beyond human comprehension. As we continue to study the universe and gather more data, we may uncover new insights into the ultimate fate of the cosmos. The discovery of new phenomena, such as the nature of dark energy, the behavior of black holes, or the potential for new forms of cosmic evolution, could reshape our understanding of the universe's future. But for now, the Big Freeze stands as a sobering reminder of the universe's long-term trajectory, a universe that will continue to expand, cooling and darkening until time itself becomes irrelevant in the face of eternal stillness. In the grand scheme of things, the Big Freeze is but one possible outcome in the ongoing saga of cosmic evolution. It may seem like a bleak and inevitable end, but it is also a testament to the vast, inexorable forces that shape the universe. The future of the cosmos, like its past, is a story of expansion, change, and transformation. And while the ultimate end may be a frozen void, the journey of the universe will continue to inspire and awe generations of scientists, philosophers, and curious minds for eons to come. The Big Crunch is one of the most fascinating and dramatic scenarios for the eventual end of the universe. This theory suggests that, instead of continuing to expand indefinitely, the universe could eventually slow down, reverse its expansion, and collapse in on itself, leading to a dramatic and catastrophic conclusion. The Big Crunch would mark the ultimate return to a singularity, a point of infinite density and temperature, a cosmic implosion of unimaginable proportions. The concept of the Big Crunch is deeply tied to the idea of gravitational forces and the dynamics of the universe's expansion. According to the Big Bang theory, the universe began from a singularity and has been expanding ever since. In the early stages, this expansion was rapid and violent, but over time, the universe has gradually slowed as the gravitational pull of matter has worked to counteract the expansion. For most of the universe's history, this slowing expansion has been countered by the force of dark energy, which has accelerated the expansion since the late 20th century. However, the Big Crunch theory proposes that the balance between expansion and gravity could shift, leading to a reversal of this trend. At the heart of the Big Crunch theory is the question of the total mass of the universe. In classical physics, it is often thought that the universe's expansion could eventually be slowed, halted, and reversed if the gravitational pull of all the matter in the universe is strong enough. In this scenario, the matter in the universe would act like a cosmic brake, eventually slowing the expansion of the universe and causing it to collapse under its own weight. The more mass there is in the universe, the stronger the gravitational pull, and the more likely it is that the universe will contract. The Big Crunch scenario depends on the balance between two competing factors: the gravitational pull of all the matter in the universe and the force of dark energy, which is currently driving the accelerated expansion. If the gravitational pull of matter is stronger than the repulsive force of dark energy, the expansion of the universe will eventually slow, stop, and reverse, leading to a contraction. Conversely, if dark energy dominates the universe's expansion, the universe will continue to accelerate outward indefinitely, and the Big Crunch will not occur. The ultimate fate of the universe in this context hinges on the relative strengths of these two forces. One of the key pieces of evidence for the Big Crunch theory lies in the measurement of the universe's density. In order for the universe to collapse under the force of gravity, its total mass or density must exceed a critical threshold. This threshold, often referred to as the critical density, is the amount of mass that would cause the universe to slow its expansion and eventually reverse it. If the density of the universe is lower than this critical value, the expansion will continue indefinitely, leading to a scenario like the Big Freeze. If the density exceeds the critical density, gravity will eventually overcome the expansion, and the universe will contract in a Big Crunch. For many years, scientists believed that the universe's fate was tied to its density. Observations suggested that the universe's density was too low to reverse the expansion, and that the Big Crunch was unlikely. However, the discovery of dark energy in 1998 added a new layer of complexity to this picture. Dark energy, a mysterious form of energy that makes up about 68% of the universe's total energy content, is thought to be driving the accelerated expansion of the universe. The repulsive effect of dark energy has caused the universe's expansion to speed up, counteracting the gravitational forces that would normally slow it down. Since the discovery of dark energy, the possibility of the Big Crunch has become less likely. If dark energy continues to dominate the universe's expansion, the universe will keep expanding indefinitely, leading to a Big Freeze. But the existence of dark energy does not rule out the Big Crunch entirely. If dark energy were to change over time, for instance, if its influence weakened or disappeared, the expansion of the universe could slow and reverse, making the Big Crunch scenario plausible once again. Another factor that influences the likelihood of a Big Crunch is the role of dark matter. Dark matter, which is a form of matter that doesn't interact with light but has gravitational effects on visible matter, makes up about 27% of the universe's total mass. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, so it can't be detected directly. However, its gravitational effects are observable, and scientists believe that dark matter plays a crucial role in the structure of the universe. Dark matter helps to bind galaxies and galaxy clusters together, and its gravitational influence may be an important factor in the eventual collapse of the universe. In a Big Crunch scenario, dark matter would act as a source of gravitational pull, causing the universe to contract. As galaxies and cosmic structures move closer together, the density of matter would increase and the gravitational pull of dark matter would intensify. If dark energy were to weaken or disappear, the gravitational forces of dark matter and ordinary matter could cause the universe to collapse in on itself. The Big Crunch would be a violent and chaotic event, with galaxies, stars, and planets being drawn toward a single point where the universe would return to a singularity, the state from which it began. The Big Crunch theory has fascinating implications for the ultimate fate of the universe. If the universe were to collapse, it would be the culmination of a cycle that began with the Big Bang. In this scenario, the universe would return to a state of infinite density, just as it was at the start. Time itself might collapse into a singularity where the laws of physics as we know them break down. The idea that the universe could end in the same state that it began, as a singularity, raises profound questions about the nature of time, space, and the origins of the universe. Despite the dramatic and fascinating possibilities offered by the Big Crunch, the theory faces several challenges. First, the discovery of dark energy has made the collapse of the universe seem less likely. Dark energy, which is pushing galaxies apart, appears to counteract the effects of gravity, making the expansion of the universe accelerate. This has led many scientists to believe that the Big Freeze, a universe that continues to expand indefinitely, is a more probable outcome than the Big Crunch. Additionally, the idea of the Big Crunch depends on the behavior of dark energy, which remains one of the greatest mysteries in modern cosmology. If dark energy continues to dominate the universe's expansion, the Big Crunch will not occur. However, some theories suggest that dark energy could change over time, weakening and allowing gravity to take over. This could lead to a scenario in which the universe slows down and eventually collapses. The possibility of the Big Crunch raises other intriguing questions about the ultimate fate of the universe. If the universe were to collapse, could it be followed by another Big Bang, creating a cycle of creation and destruction, a kind of cosmic recycling? Some theories, such as the cyclic model of the universe, propose that the universe undergoes an eternal series of expansions and contractions. In this model, each Big Crunch would lead to a new Big Bang, starting the cycle over again. While this idea is speculative, it suggests that the universe may not have a single final end, but rather go through infinite cycles of birth, death, and rebirth. Another possibility is that the Big Crunch could be accompanied by quantum effects that we do not yet fully understand. At the extreme densities and temperatures of a collapsing universe, quantum gravity may play a crucial role. The study of quantum gravity, which seeks to reconcile general relativity with quantum mechanics, may offer new insights into the behavior of the universe at the smallest scales. If quantum effects are involved in the Big Crunch, it could lead to the creation of new structures or even new universes, a possibility that would radically change our understanding of the cosmos. In the end, while the Big Crunch remains an intriguing and dramatic possibility, it is just one potential outcome in the larger story of the universe. The discovery of dark energy and the accelerated expansion of the universe have shifted our focus toward the Big Freeze, but the ultimate fate of the cosmos is still uncertain. Whether the universe continues to expand and cool, collapses in on itself, or undergoes some other transformation, the journey of cosmic discovery is far from over. The question of how the universe will end is not just a matter of physics, It is a profound philosophical and existential question that challenges us to think about our place in the vast expanse of time and space. The Big Crunch offers a vision of the universe's end that is both terrifying and awe-inspiring. It is a reminder of the immense forces that shape the cosmos and the finite nature of everything we know. But even as we ponder the end of time, we must remember that the universe is still in the midst of its journey. The fate of the cosmos is yet to be determined, and as we continue to explore the mysteries of the universe, we move ever closer to understanding the true nature of time, space, and the forces that will shape the universe's final chapter. Among the various theories regarding the ultimate fate of the universe, the Big Rip stands out as one of the most dramatic and cataclysmic possibilities. Unlike the gradual cooling and fading of the Big Freeze or the cyclic collapse of the Big Crunch, the Big Rip presents a universe whose expansion accelerates to the point where everything, from galaxies to atoms, is torn apart by the very fabric of space-time itself. If this scenario comes to pass, it would be an unimaginable end, a final, irreversible unraveling of the universe in a cosmic event of unimaginable scale and violence. The idea of the Big Rip is rooted in the ongoing expansion of the universe, which was first observed by astronomers in the late 20th century. As we discussed in earlier chapters, the discovery that the universe's expansion is accelerating, rather than slowing down as once predicted, radically altered our understanding of the cosmos. This accelerated expansion is attributed to dark energy, a mysterious force that accounts for about 68% of the universe's total energy content. While dark energy is responsible for the accelerated expansion of the universe, its true nature remains elusive, and its long-term effects are still the subject of intense study and speculation. The Big Rip theory proposes that, over time, the influence of dark energy will become so powerful that it will overwhelm the gravitational forces that hold galaxies, stars, and even atoms together. As dark energy drives the expansion of space to ever-increasing speeds, the distance between galaxies will continue to grow, and eventually, the expansion will reach a point where it begins to tear apart all cosmic structures. The underlying mechanism of the Big Rip is the stretching of space-time itself, which becomes increasingly pronounced as the universe expands. As space-time stretches, objects within the universe, including galaxies, stars, planets, and even the fundamental particles that make up matter, will be pulled apart one layer at a time. The timeline for the Big Rip depends on the properties of dark energy and the rate at which the universe continues to expand. The key factor is the equation of state of dark energy, a measure of how dark energy's density changes over time. In the simplest model of dark energy, the cosmological constant introduced by Einstein in the early 20th century, dark energy's influence remains constant and the expansion of the universe accelerates at a steady rate. In this scenario, the Big Rip could occur in about 22 billion years, far in the future, but within the cosmic timescale. However, more complex models of dark energy suggest that its influence could grow stronger over time, leading to an even earlier and more dramatic end. In the Big Rip scenario, as the universe's expansion accelerates, galaxies will move farther apart and the gravitational forces that bind them together will become weaker. Eventually, galaxies will become isolated and their stars will drift away from each other, unable to interact. The Milky Way, for example, will no longer be able to interact with other galaxies as its distance from them increases. This process will be a slow one, taking billions of years, but over time, the universe will become increasingly empty and dark as galaxies are stretched apart. As the expansion continues to accelerate, it will eventually reach the point where the forces of gravity within galaxies themselves can no longer hold them together. This is where the true chaos of the Big Rip begins. The gravitationally bound systems, like galaxies, solar systems, and even the Earth, will begin to break apart. First, the individual stars within galaxies will be torn from their orbits as the space between them expands. Planets, moons, and all objects within these galaxies will be separated, driven apart by the stretching of space-time. The once vibrant, organized cosmos will disintegrate into a scattered, disordered state, with stars and planets becoming isolated, their connections to one another severed by the relentless expansion. The destruction of solar systems and galaxies will not be the end, however. As the universe continues to expand, the very forces that hold atoms and molecules together, the electromagnetic force and the strong and weak nuclear forces, will eventually be overcome by the stretching of space-time. Atoms themselves will be torn apart as the expansion becomes so extreme that the bonds between subatomic particles are no longer strong enough to hold them together. Electrons will be ripped from their nuclei, and protons and neutrons will be separated. Even the most fundamental building blocks of matter will be stretched and fragmented by the accelerating expansion. Eventually, the universe will reach a point where even the fundamental forces that govern space and time cannot prevent the destruction of all structure. In the final moments of the Big Rip, everything will be torn apart, leaving nothing but a cold, empty, and expanding universe. This final stage represents the ultimate disintegration of the universe, where no matter, no light, and no energy remain. The universe, once full of galaxies, stars, and the potential for life, will have dissolved into nothingness, consumed by the unstoppable force of dark energy. While the Big Rip presents a vision of ultimate destruction, it is not an outcome that is inevitable, at least, not yet. The Big Rip depends on the behavior of dark energy, and there are still many unknowns about how dark energy will evolve over time. If dark energy remains constant, the universe will continue expanding at an accelerating rate, and the Big Rip could eventually occur. However, if dark energy weakens or if its influence diminishes in some way, the expansion of the universe could slow down, and the Big Rip might never happen. One of the challenges in predicting the fate of the universe is that we do not fully understand dark energy's nature or behavior. While we can observe the effects of dark energy on the expansion of the universe, we do not yet know why it exists or what drives its repulsive force. Some theories suggest that dark energy could change over time, while others propose that it is a fundamental, unchanging property of the universe. Until we gain a better understanding of dark energy, we can only speculate about how it will affect the future of the cosmos. In addition to dark energy's role in the Big Rip, there are other factors that could influence the fate of the universe. For example, quantum effects at the smallest scales might have an impact on the dynamics of space-time. The study of quantum gravity, which seeks to combine the principles of quantum mechanics with general relativity, may offer insights into how the universe's expansion could evolve. Some quantum theories propose that space-time itself could undergo phase transitions, or that the laws of physics could change under extreme conditions, potentially altering the course of the universe's expansion. In the grand scheme of cosmic time, the Big Rip is still a distant event. It's not something that will occur for billions of years. However, the potential for such a catastrophic end raises profound questions about the nature of the universe and the forces that govern it. The Big Rip challenges our understanding of the cosmos, suggesting that the universe's ultimate fate could be determined by forces that we do not yet fully comprehend. If the Big Rip were to occur, it would mark the final chapter in the universe's history. It would be the ultimate end of time, as we know it, and a fitting conclusion to the universe's journey from birth to destruction. The destruction of everything, from galaxies to atoms, would be an event on a scale so immense that it is hard to imagine. Yet, even in this final moment, there may be something to learn about the nature of the universe and the forces that shaped it. The Big Rip, if it happens, will leave behind a universe that is nothing like the one we see today, a universe that will have expanded into an infinite, empty void. The possibility of the Big Rip raises profound existential and philosophical questions about the ultimate nature of time, space, and reality. It forces us to confront the impermanence of the universe and the fleeting nature of existence. But even in the face of this ultimate destruction, the Big Rip also offers a reminder of the vastness of cosmic time, a reminder that the universe is vast, dynamic, and unpredictable, with forces at work far beyond our comprehension. As we continue to study dark energy, space-time, and the forces that shape the universe, we may uncover new insights into the potential for the Big Rip, or perhaps find evidence for other outcomes entirely. The future of the universe is still uncertain, but one thing is clear. The cosmos will continue to evolve, and the quest to understand its fate is an ongoing journey that will continue to inspire and challenge scientists for generations to come. The idea of the cyclic universe, or eternal recurrence, proposes that the universe might not have a single beginning or end. Instead, it suggests that the cosmos undergoes an infinite series of expansions and contractions, each cycle beginning with a big bang and ending with a big crunch, only to start again in an endless loop. This concept challenges the conventional view of the universe's life cycle, which assumes a linear progression from birth to death and offers a radically different perspective on the fate of the cosmos. In this chapter, we will explore the fascinating and controversial theory of the cyclic universe and examine the evidence and ideas that support this model. The idea of a cyclic or oscillating universe has ancient roots, dating back to early philosophical and cosmological speculations. Ancient Indian and Greek philosophers, such as Heraclitus and Buddhist cosmology, conceived of the universe as undergoing cycles of creation and destruction. However, the modern version of the cyclic universe was first seriously proposed in the 20th century, particularly with the advent of general relativity and cosmology. Early in the 20th century, physicists like Alexander Friedmann and Georges Lemaitre suggested that the universe could be dynamic, with a beginning and an end, but they did not yet propose that it would undergo an eternal series of cycles. The modern theory of the cyclic universe draws heavily on ideas from general relativity and quantum mechanics, as well as observations of the large-scale structure of the cosmos. It is built around the concept of a closed universe, one in which the total density of matter and energy is high enough to eventually halt the universe's expansion and reverse the process. This would lead to the Big Crunch, where the universe collapses back in on itself, only to start the cycle again with another Big Bang. The idea is similar to the bouncing universe model, where the universe repeatedly expands and contracts in an infinite cycle. The most well-known modern version of the cyclic universe model is the ekpyrotic universe theory, which was proposed in the early 2000s by cosmologists Paul Steinhardt and Neil Turok. This model suggests that our universe is the result of a collision between two branes, multidimensional objects, in a higher dimensional space. In this scenario, the universe undergoes periodic cycles, with each cycle starting with a collision between these branes, creating a Big Bang, and ending with the collapse of the branes into a Big Crunch. This cycle could repeat indefinitely, with each new cycle representing a fresh beginning for the universe. While the ekpyrotic model has gained some attention in the scientific community, it remains highly speculative and it has yet to be confirmed by observational data. In fact, many cyclic models of the universe face significant challenges when it comes to explaining how the universe could sustain such an eternal cycle. One of the most pressing questions is how the universe could return to the same state after each cycle. In the standard Big Bang theory, the universe's expansion leads to the creation of matter, energy, and structures that evolve over time. A cyclic model would need to account for the fact that the universe is not the same as it was in previous cycles. Stars, galaxies, and black holes are not simply reset at the start of each new cycle. Despite these challenges, the cyclic universe theory has received considerable interest because it offers a potential solution to some of the most perplexing questions in cosmology. For example, one of the central mysteries of the universe is the problem of fine-tuning. The fundamental constants of nature, such as the strength of gravity, the mass of particles, and the speed of light, appear to be perfectly tuned to allow for the existence of life and the formation of galaxies. If any of these constants were even slightly different, the universe would be vastly different, and life as we know it would be impossible. The question then arises, why are these constants so finely tuned? In a cyclic universe, this fine-tuning could be explained by the repeated cycles of cosmic evolution. Each new cycle might reset the universe, leading to the same set of conditions that allow for life to emerge. The multiverse theory is also often linked to the concept of the cyclic universe. According to some models, the universe we observe is just one of many that exist in a vast multiverse of parallel worlds. Each time the universe undergoes a Big Bang, it creates a new bubble universe, which could have different physical laws and constants. In this scenario, the multiverse becomes an ever-expanding collection of universes that are constantly being born and dying, with each universe going through its own cycle of expansion and contraction. This theory has the potential to explain the fine-tuning of the universe, as the vast number of universes in the multiverse increases the likelihood that at least one of them will have the right conditions for life to emerge. However, the concept of a cyclic universe also raises deep philosophical questions. If the universe is constantly being reborn, does this imply an infinite number of previous cycles? And if the universe is eternal, what does this mean for the concept of time? In the traditional Big Bang model, the universe has a beginning, a moment when time itself began. But in a cyclic universe, time might not be linear. Instead, it could be circular, with no definitive beginning or end. This raises questions about the nature of time, causality, and existence itself. If the universe is endlessly reborn, does this mean that everything that has happened or will happen has already occurred in previous cycles? Is there a deeper meaning to these cycles, or are they simply a natural process of cosmic evolution? The cyclic universe theory also challenges our understanding of entropy. In the traditional Big Bang model, the universe began in a low entropy state and has been increasing in entropy ever since. According to the second law of thermodynamics, entropy will continue to increase, leading to the eventual heat death of the universe. In a cyclic universe, however, the question arises, how does entropy reset after each cycle? The increase in entropy seems to suggest that the universe's expansion must eventually come to an end. But the cyclic model must reconcile this with the idea of an eternal series of cycles. Some scientists have proposed that the universe could undergo a quantum bounce, where the entropy from one cycle is reset at the start of the next cycle, avoiding the buildup of entropy that would otherwise lead to the universe's destruction. Despite the challenges of the cyclic model, it has the advantage of offering a potential solution to some of the mysteries that arise from the standard Big Bang theory. For example, the cyclic universe provides a natural explanation for the flatness problem and the horizon problem, two issues that arise when we consider the large-scale structure of the universe. In the traditional Big Bang model, the early universe must have been in a state of extremely low entropy. But how could this low entropy state arise from a random quantum fluctuation? In the cyclic universe model, the repeated cycles of expansion and contraction could help explain the low entropy state of the early universe and provide a mechanism for its evolution. While the cyclic universe remains speculative, it is an intriguing theory that challenges our understanding of cosmology and the nature of time. As our understanding of dark energy, quantum mechanics, and the fundamental forces of nature continues to grow, we may one day be able to test the validity of the cyclic model and determine whether the universe truly undergoes an infinite series of cycles. For now, the theory provides an exciting glimpse into the possibility of a universe that is not bound by a single beginning and end, but instead exists in an eternal cycle of creation, destruction, and rebirth. As we continue to explore the cosmos and uncover the secrets of the universe's past, present, and future, the concept of the cyclic universe offers a powerful framework for thinking about the ultimate fate of the cosmos. It challenges our assumptions about the nature of time and the beginning and end of the universe, pushing the boundaries of our understanding and inviting us to consider new possibilities for the universe's destiny. Whether the cyclic model is ultimately proven true or not, it serves as a reminder of the vast mysteries that still await discovery and the limitless potential of human curiosity and exploration. As we contemplate the eventual end of the universe, it becomes increasingly apparent that quantum mechanics plays a crucial role in how we understand time itself and how the universe might ultimately meet its fate. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, is both extraordinarily successful and deeply mysterious. It describes a reality that defies classical intuition, where particles can exist in multiple states simultaneously, and where the very act of observation can influence the outcome of events. As we move closer to understanding the ultimate fate of the universe, quantum mechanics challenges our perceptions of time, causality, and even the nature of reality itself. At its core, quantum mechanics is built on a foundation of uncertainty and probability. Unlike classical physics, where the behavior of objects can be predicted with a high degree of certainty, quantum mechanics operates on the principle that particles can exist in multiple states at once, and only when they are measured do they collapse into a single state. This principle, known as superposition, suggests that the universe at the quantum level is constantly in flux, a blur of possibilities that only solidify into definite outcomes when observed. The famous Schrödinger's cat thought experiment illustrates this concept. A cat locked in a box with a radioactive atom can be considered both alive and dead at the same time, until someone opens the box to observe its state. This paradox challenges our conventional understanding of reality and time. The uncertainty at the quantum level is not just a philosophical or theoretical issue. It has real, measurable effects on the behavior of particles. The Heisenberg uncertainty principle states that there is a fundamental limit to how precisely we can measure certain pairs of properties of a particle, such as its position and momentum. This principle introduces an inherent fuzziness into our understanding of particles and the flow of time. In classical physics, we might expect that if we know the current state of a system, we can predict its future behavior. However, in quantum mechanics, the future is probabilistic, not deterministic. This means that, on a fundamental level, time itself is not as straightforward as we might think. In addition to the uncertainty principle, quantum mechanics also introduces the concept of quantum entanglement, a phenomenon in which two particles become linked in such a way that the state of one particle is instantly connected to the state of the other, no matter how far apart they are. This connection happens faster than the speed of light, leading Einstein to famously refer to it as spooky action at a distance. Quantum entanglement challenges our classical understanding of causality and time, suggesting that particles, and by extension, the universe, may be fundamentally interconnected in ways that transcend space and time as we perceive them. The implications of quantum entanglement are profound, particularly when we consider the possible fate of the universe. If the quantum realm can link distant parts of the cosmos in such an instantaneous manner, could this imply that the boundaries of time and space as we understand them may not be fixed? Could the end of time be something entirely different than what we expect, influenced by quantum processes that we do not yet fully comprehend? The role of quantum mechanics in the ultimate fate of the universe becomes even more relevant when we consider the concept of quantum gravity, the elusive theory that seeks to unify quantum mechanics with general relativity, the theory that describes the force of gravity and the large-scale structure of the universe. For decades, physicists have struggled to reconcile these two frameworks as they describe reality at vastly different scales. Quantum mechanics governs the tiny world of particles and atoms, while general relativity governs the vast scales of galaxies, stars, and black holes. The two theories are incompatible in their current forms, and the search for a unified theory of quantum gravity is one of the most important challenges in modern physics. The need for quantum gravity becomes especially apparent when we consider the behavior of black holes. Black holes are regions of space where gravity is so strong that not even light can escape. According to general relativity, black holes are formed when a massive star collapses under its own gravity, creating a singularity, a point of infinite density where space-time curves infinitely. But when we apply the principles of quantum mechanics to black holes, we run into a paradox. The laws of quantum mechanics suggest that information cannot be lost, but according to general relativity, the information inside a black hole is irretrievably lost once it crosses the event horizon. This has led to the black hole information paradox, one of the biggest unresolved problems in theoretical physics. Could the resolution of this paradox provide insights into the nature of time and the ultimate fate of the universe? Quantum mechanics may also provide a clue as to why time behaves the way it does on large scales. At the quantum level, time is not always treated as a fundamental linear progression. Some theories of quantum gravity suggest that time itself may be an emergent property of the universe, arising from the interactions between quantum fields. In this view, time is not a fixed, fundamental quantity, but rather a result of the relationships between particles and fields. This raises the possibility that time, as we experience it, is not as fundamental as space and energy. Could time itself be something that is not inherent to the universe, but instead arises from the conditions within it? If so, this could have profound implications for how we understand the beginning and end of time. One of the most intriguing ideas in quantum mechanics is the possibility that time itself could end, not just in the sense of the universe becoming a cold, empty void, but in the fundamental sense that time as a dimension could cease to exist. This concept is explored in various theories of quantum cosmology, which attempt to describe the early moments of the universe using quantum mechanics. According to some models, the universe may have begun as a quantum fluctuation in a timeless, spaceless void. In this model, time itself would not have existed prior to the Big Bang. It would have emerged as part of the creation of the universe. Could time itself one day reverse and cease to be a defining feature of the universe, especially as the cosmos reaches its final state? One possible scenario for the end of time comes from the study of black holes in quantum mechanics, which suggests that as the universe reaches a state of maximum entropy, a state where all matter and energy are evenly spread throughout space, time itself could lose its meaning. As black holes continue to evaporate due to Hawking radiation and matter continues to disperse, the universe might approach a state of absolute equilibrium. In this scenario, time would no longer have any measurable effects, and the universe would exist in a state of stasis, where no events, no changes, and no distinctions between past, present, and future could be made. Time, as we understand it, would essentially come to an end in this final state of cosmic stillness. Quantum mechanics also opens the door to alternative views of the end of time. One such theory is the many worlds interpretation of quantum mechanics, which proposes that every quantum event spawns a new parallel universe. According to this theory, the universe we observe is just one of an infinite number of possible realities, and the course of time might be radically different in each one. This raises the question, if time behaves differently in different worlds, could the concept of an end be entirely subjective, with each universe following its own trajectory? Is the end of time a universal concept, or could it be different depending on the quantum history of each individual universe? As we look ahead to the ultimate fate of the universe, the role of quantum mechanics cannot be overstated. Quantum mechanics challenges our most basic intuitions about the nature of time, space, and reality. The possibilities it presents for the end of time, from the collapse of space-time in a black hole to the evaporation of the universe's last particles, paint a picture of an unpredictable and mysterious conclusion. While the traditional models of the Big Freeze, Big Crunch, and Big Rip offer compelling visions of the universe's eventual end, quantum mechanics suggests that the fate of time itself might be far more complicated and potentially far stranger than we can currently imagine. As we continue to explore the universe through the lens of quantum mechanics, we may uncover even more profound truths about the nature of time. Whether time is an emergent property of the universe, a quantum fluctuation, or an inherent part of the fabric of reality, our understanding of time will shape our understanding of the universe's ultimate fate. And as we move closer to understanding the quantum nature of the cosmos, we may find that time, as we know it, is not as fixed or final as we once believed. As we explore the ultimate fate of the universe, we are confronted with one of the most profound and elusive questions. What role does consciousness play in our understanding of time, and how does it affect our perception of time's end? While cosmologists and physicists strive to describe the universe's future through the lens of entropy, dark energy, and quantum mechanics, The human experience of time is far more complex. We perceive time not only as a continuous flow, but as a subjective experience that is deeply connected to our sense of being. As we seek to understand the final stages of the universe, we must also consider how the end of time might relate to consciousness itself, a question that transcends physics and enters the realm of philosophy, psychology, and the very essence of existence. The nature of consciousness has puzzled philosophers, scientists, and mystics for centuries. What is consciousness? Is it a byproduct of complex brain activity, or is it something more fundamental, a core feature of the universe itself? In modern science, consciousness is often thought of as the product of the brain's neural processes. Our thoughts, emotions, and perceptions arise from the interactions of neurons in the brain, and it is through these interactions that we experience time. Our consciousness allows us to be aware of the passage of time, to remember the past, and to anticipate the future. Yet, despite the advances in neuroscience, we still lack a comprehensive theory of consciousness, and this gap in our understanding becomes particularly relevant when we think about the end of time. In the context of the universe's end, consciousness becomes an even more intriguing concept. If the universe eventually reaches a state of maximum entropy, a point where all matter is evenly distributed and no energy can be used to drive processes, what will be the role of consciousness? Will there still be beings capable of experiencing time in any meaningful way? Or will the end of time represent a true cessation of awareness? Will consciousness itself cease to exist as the universe becomes an eternal lifeless void? The prospect of time ending and the universe becoming a frozen, still place raises difficult questions about the future of sentient beings and their ability to perceive the universe. Before we address these questions, it's important to consider how consciousness interacts with the flow of time. Our understanding of time is intimately tied to our perception of it. Time is something we experience on a deeply personal level, and our minds are constantly processing the passage of time, creating memories of the past, experiencing the present, and projecting ourselves into the future. Our ability to track time, anticipate future events, and learn from past experiences is central to the way we navigate the world. Without this conscious awareness of time, our experience of existence would be fundamentally different. One of the most fascinating aspects of consciousness and time is the relationship between subjective time and objective time. While objective time refers to the measurable passage of time, the ticking of the clock, the turning of the seasons, the lifespan of a star, subjective time is the way we experience time on a personal level. Subjective time is not constant. It can feel as though time speeds up when we are engaged in a stimulating activity or slows down when we are waiting for something. Our perception of time is influenced by our state of consciousness, our attention, and our emotional state. This makes time something more than just a scientific concept. It is an intrinsic part of what it means to be alive and aware. But what happens when the universe reaches its final state? If the big freeze occurs and the universe continues to expand, cooling and becoming increasingly dark, will time as we experience it lose its meaning? If no processes can take place and no changes occur, will there still be a flow of time? The ultimate end of time, as described by the big freeze or other scenarios, seems to suggest a stasis, a universe where no events unfold and everything remains frozen in place. For conscious beings, this would represent a complete loss of the experience of time. Without change, memory, or anticipation, the subjective experience of time would cease to exist, and consciousness itself might be rendered meaningless. However, this idea raises another profound question. Is consciousness something that depends entirely on the passage of time, or could it exist independently of it? Some philosophical and spiritual traditions suggest that consciousness is not bound to the linear flow of time. In these traditions, consciousness is often viewed as an eternal, unchanging force, something that transcends the limitations of the physical world. In the context of the universe's end, this perspective might offer a different view of time's conclusion. If consciousness is not tied to the material world, it may continue to exist even after the physical universe reaches its end. This view aligns with certain interpretations of quantum consciousness theories, which propose that consciousness could be a fundamental property of the universe, just as gravity or electromagnetism is. If this is the case, consciousness might persist even in a universe that has reached a state of maximum entropy, an idea that challenges our conventional understanding of both time and existence. One intriguing possibility that arises from the relationship between consciousness and time is the concept of eternal recurrence, the idea that time and events might not truly end, but rather repeat in an endless cycle. This idea has roots in ancient philosophy, particularly in the writings of Friedrich Nietzsche, who posited that the universe might undergo a perpetual cycle of birth, death, and rebirth. In Nietzsche's view, eternal recurrence was not merely a physical event, but a spiritual one, a way for individuals to embrace the totality of life, including its suffering and joy. In the context of the end of time, this idea suggests that consciousness itself might be linked to an infinite cycle of experiences, with time and existence endlessly repeating. The notion of eternal recurrence offers a stark contrast to the idea of the heat death or big freeze, which envisions an end to time and consciousness. In the eternal recurrence model, time does not end. It simply cycles, and consciousness is carried along with it. This perspective offers a more hopeful vision of the universe's end, one where the total destruction of the universe is not the final chapter, but rather the beginning of something new, a continuous cycle of rebirth and renewal. While this idea remains speculative and philosophical, it highlights the potential for time to be far more complex and cyclical than we currently understand. From a more scientific perspective, the future of consciousness and time is still deeply intertwined with the fate of the universe. If the universe continues to expand and eventually reaches a state of maximum entropy, what happens to the possibility of conscious beings? If the heat death scenario unfolds and no usable energy remains, it is hard to imagine how consciousness could persist. However, there are some who argue that if consciousness is a quantum phenomenon, as some proponents of quantum consciousness suggest, it might not be strictly tied to the physical state of the universe. Quantum mechanics, with its mysterious nature, might offer a way for consciousness to transcend physical constraints, potentially continuing beyond the death of the universe in a state that we cannot yet understand. Ultimately, the relationship between time and consciousness is one of the most profound mysteries we face as we contemplate the universe's end. While our scientific understanding of time, entropy, and the cosmos provides us with a framework for imagining the future of the universe, the role of consciousness complicates this vision. Consciousness is not simply a passive observer of time's passage. It actively participates in shaping our experience of the universe. Without consciousness, time would have no meaning. As we approach the end of time, the question of whether consciousness can survive the death of the universe challenges us to think about existence in ways that transcend science. In the grand scheme of cosmic time, the ultimate fate of the universe may be cold, dark, and final. Yet, the question of whether consciousness will endure and how time itself will be perceived in such a scenario remains a profound and deeply personal one. Whether consciousness is eternal or bound to the physical universe, the end of time will mark the conclusion of an era in our understanding of reality, leaving us to ponder the mysteries of existence long after the universe has ceased to function as we know it. The fate of the universe is often described in terms of time, entropy, and matter, but one aspect that should not be overlooked in these considerations is space itself. Just as time is not a fixed entity in the universe, neither is space. In fact, space, the very fabric that stretches and contracts, bends and warps, plays a critical role in shaping the universe's destiny. As we explore the ultimate fate of the cosmos, we must also consider what happens to space as the universe approaches its end, whether through the big freeze, the big crunch, the big rip, or some other cataclysmic event. Space, as we understand it, is not an empty void. It is a dynamic, ever-changing entity that is deeply connected to the matter and energy that reside within it. Albert Einstein's theory of general relativity, revolutionized our understanding of space by showing that it is not simply a backdrop for the universe's events, but an active participant in the cosmic drama. Space is intertwined with time to form what we call space-time, a four-dimensional fabric that can bend and stretch in response to the presence of matter and energy. This warping of space-time is what causes gravity, the force that keeps planets in orbit, pulls light towards black holes, and governs the motion of galaxies. In the early 20th century, the realization that space itself could be warped by gravity opened the door to a completely new way of thinking about the universe. The expanding universe model, which arose from observations of distant galaxies moving away from us, revealed that space itself is stretching over time. The distance between objects in the universe is not simply increasing because the objects are moving through pre-existing space. Rather, it is the fabric of space itself that is expanding. This expansion has been a key aspect of our understanding of the cosmos, and it will play a central role in determining the universe's ultimate fate. The expanding universe. One of the most profound discoveries in the history of cosmology was that the universe is expanding. In 1929, astronomer Edwin Hubble discovered that galaxies are moving away from each other, and the farther away a galaxy is, the faster it is receding. This observation, known as Hubble's law, provided strong evidence for the idea that the universe began from a singularity in the distant past and has been expanding ever since, a concept that became central to the Big Bang theory. But while the expansion of the universe was first measured in terms of the recession of galaxies, it became clear that this expansion is not occurring within space. Rather, it is the very fabric of space itself that is stretching. The space between galaxies is getting larger, causing galaxies to move farther apart. Over time, this expansion has slowed down due to gravitational attraction between galaxies, but the discovery of dark energy in the late 20th century revealed that the expansion is actually accelerating. The role of dark energy in space's future. Dark energy, a mysterious force that makes up about 68% of the universe's total energy content, is thought to be responsible for this accelerated expansion. Unlike gravity, which acts to pull matter together, dark energy exerts a repulsive force that pushes galaxies apart. While the exact nature of dark energy remains one of the most profound mysteries in cosmology, its effects on space-time are undeniable. Dark energy is causing the fabric of space to expand at an ever-increasing rate, and this process is having a profound impact on the future of the universe. The question then arises, if dark energy continues to drive the accelerated expansion of the universe, what will happen to space itself in the far distant future? If the expansion continues, galaxies will move farther and farther apart, and eventually, the stars within those galaxies will burn out. As the universe expands, the available energy to power stars, heat planets, and sustain life will dwindle. The universe will become an increasingly cold, dark, and empty place. But what happens to space itself as this expansion continues? The fabric of space is constantly stretching, and as it does, it carries with it everything in the universe, galaxies, stars, and even the very atoms that make up matter. As the universe expands, space becomes more and more diluted, spreading the matter and energy in the cosmos farther apart. The very structure of space-time itself will become stretched thin, until eventually there may be no recognizable structure left. In the Big Freeze scenario, space itself will continue to stretch indefinitely. Galaxies will become increasingly isolated from each other, and eventually the stars within them will burn out. The universe will be filled with dark voids where no new stars will be born and the energy that powers life will be depleted. The expansion of space will continue and the universe will gradually become a vast empty expanse with no processes or events taking place. Space and the Big Rip. If the universe continues to expand at an accelerating rate, there is a possibility that the expansion could become so extreme that it tears apart the very fabric of space-time. This is the premise of the Big Rip, a scenario in which the influence of dark energy becomes so intense that it overwhelms every force in the universe, including gravity and the strong nuclear force. In the Big Rip, galaxies will be pulled apart, stars will be torn from their orbits, and even atoms and subatomic particles will be ripped apart as the expansion accelerates beyond all control. In this scenario, space itself will undergo a dramatic and violent transformation. The forces that bind galaxies together, such as gravity, will no longer be able to resist the overwhelming push of dark energy. As space stretches faster and faster, it will cause the universe to unravel, piece by piece. First, galaxies will be ripped apart, followed by the solar systems within them. As the expansion accelerates, the force of dark energy will overcome the gravitational forces within galaxies, causing stars to drift apart, planets to separate from their orbits, and even black holes to be pulled apart. The final stages of the Big Rip would be truly catastrophic for space itself. As dark energy grows stronger, it will stretch the very fabric of space-time, leading to the breakdown of matter itself. Atoms, the fundamental building blocks of matter, will be torn apart. Electrons will be ripped from their nuclei, and protons and neutrons will be separated. Eventually, even the most fundamental particles in the universe will be torn asunder by the expanding fabric of space. In this scenario, space will no longer have any recognizable structure. It will become a chaotic and fragmented expanse with nothing left to hold it together. The Big Crunch and space's contraction. While the Big Rip suggests an infinite stretching of space, the Big Crunch offers a completely different fate for space itself. In the Big Crunch scenario, the universe would reverse its expansion and collapse in on itself due to the gravitational attraction of all the matter and energy in the cosmos. Instead of space stretching endlessly, it would begin to contract, drawing galaxies, stars, and planets back together. The contraction of space would be a dramatic process. As galaxies moved closer together, the gravitational forces would increase, pulling stars and other objects toward one another. This cosmic collapse would lead to the destruction of all structure, as matter and energy are squeezed into a singularity, a point of infinite density. In this scenario, space would effectively shrink, collapsing down into an incredibly small volume, perhaps back to the same state it was in at the beginning of the Big Bang. However, the concept of a Big Crunch depends heavily on the amount of matter in the universe. If the universe contains enough mass to reverse its expansion, space would contract, leading to a final collapse. If there is not enough mass, then the expansion would continue indefinitely, and the Big Crunch would never occur. The discovery of dark energy, which is causing the accelerated expansion of the universe, has made the Big Crunch scenario increasingly unlikely, but it still remains a theoretical possibility in certain models of the universe. Space in the context of quantum mechanics. Space-time itself is not just a passive stage for the events of the universe, it is an active participant in the dynamics of the cosmos. Quantum mechanics tells us that space and time are interconnected and that the fabric of space-time itself is subject to the same quantum fluctuations that govern the behavior of particles. At the quantum level, space-time is not smooth and continuous, but rather granular and fluctuating. These fluctuations could have a profound effect on the way space behaves, particularly in extreme conditions like the end of the universe. Some quantum theories, such as loop quantum gravity, propose that space-time is made up of discrete quantized units. In this view, space is not an infinitely smooth, continuous entity, but is composed of tiny chunks of space-time. This idea has important implications for the fate of space itself. If space-time is quantized, it may not be able to stretch infinitely, as the Big Rip suggests. Instead, it might have an inherent limit to its expansion or contraction. Similarly, space-time might behave differently in the extreme environments of black holes or at the very beginning of the universe, leading to new insights into the nature of space and time. The end of space-time. As the universe continues to expand and evolve, it is clear that space itself is subject to the same cosmic forces that govern the universe's fate. Whether through the endless stretching of the Big Rip or the eventual contraction of the Big Crunch, space will undergo dramatic changes as the universe reaches its end. If the universe continues to expand indefinitely, space will eventually become so stretched and diluted that the very concept of space may lose its meaning. If the universe collapses, space will shrink and fold back into a singularity, where the laws of physics break down and space as we understand it may cease to exist. As we explore the ultimate fate of the universe, it is clear that space is not a fixed, static backdrop, but a dynamic and evolving entity. The fate of space, like the fate of time and matter, is intimately connected to the forces that shape the cosmos. In the end, space will either continue to stretch into an infinite void or collapse into a singularity. Either way, the universe's destiny will be marked by a profound transformation of space itself. The end of time and space may be a concept beyond our current understanding, but as we continue to probe the depths of the cosmos, we move ever closer to uncovering the ultimate fate of the universe. As we stand at the edge of our understanding, contemplating the vastness of the universe and the eventual fate of everything within it, we are forced to confront one of the deepest, most profound questions in all of science. What will happen to the universe? While we have made tremendous strides in understanding the forces that govern the cosmos, the final answer to the universe's ultimate fate remains uncertain. Will it expand forever in the Big Freeze, collapse in on itself in the Big Crunch, or be torn apart in the Big Rip? Or is there some other fate, entirely unforeseen, that awaits the universe? In this final chapter, we attempt to synthesize the many possibilities for the end of the universe, each based on different assumptions about dark energy, gravity, and the fundamental nature of space-time. As we examine these potential outcomes, we will also consider the larger questions they raise about the nature of existence, the role of time, and the limits of human knowledge. The fate of the universe. Recapping the possibilities. Before we dive into the ultimate possibilities, let's first review the three primary scenarios that cosmologists have proposed as the likely outcomes for the universe's fate. 1. The Big Freeze, heat death. This scenario assumes that the universe will continue to expand indefinitely, driven by the force of dark energy. As galaxies move farther apart and stars burn out, the universe will become colder and darker. Over an unimaginable time span, all processes will grind to a halt, stars will die, black holes will evaporate, and the universe will reach a state of maximum entropy, where no usable energy remains and nothing changes. The universe will become a vast, dark, and empty void, where time will continue but will hold no meaning. This represents the ultimate end of the universe as a place of dynamism, life, and change. 2. The Big Crunch. In contrast to the Big Freeze, the Big Crunch posits that the universe's expansion will eventually slow down, halt, and reverse. Gravity will overcome the repulsive force of dark energy, causing the universe to collapse inward. As galaxies, stars, and other matter draw closer together, the universe will condense into a singularity, the same point from which it began. The Big Crunch represents a cyclic model of the universe, where time and space reset, possibly leading to another Big Bang and the birth of a new cosmos. This scenario implies that the universe undergoes an eternal cycle of expansion and contraction with no definitive end, only a continual rebirth. 3. The Big Rip. The Big Rip theory takes the accelerated expansion of the universe to its extreme, suggesting that dark energy will eventually become so dominant that it will tear apart all cosmic structures. Galaxies, stars, planets, and even atoms will be ripped apart as space itself stretches faster than gravity and other forces can hold things together. The Big Rip would be a violent and catastrophic conclusion, with the fabric of space-time itself unraveling in a final destructive event. This scenario suggests a universe that grows increasingly unstable, culminating in its complete dissolution. While these three scenarios dominate the conversation, there are also alternative ideas and nuances to each one. For instance, the concept of the cyclic universe, in which the universe undergoes infinite cycles of birth, death, and rebirth, presents a more optimistic view, though it remains speculative. The possibility of quantum fluctuations, new dimensions of space-time, and the still mysterious nature of dark energy also leave room for other, yet undiscovered, outcomes. The role of time in the universe's fate. One of the most fascinating aspects of contemplating the end of the universe is the role of time itself. As we discussed in earlier chapters, time is not a simple uniform flow from past to future. It is shaped by the forces of gravity, the curvature of space-time, and the expansion of the universe. Time, in a sense, is deeply intertwined with the universe's evolution and its ultimate fate. In the Big Freeze, time continues to pass, but without any meaningful events. With no stars, no galaxies, and no processes to measure time against, the concept of time becomes increasingly abstract. It continues to tick forward, but it no longer serves as a measure of change. The heat death of the universe represents a timeless void, a place where time itself becomes irrelevant, as no new information is created and no energy is left to drive any processes. In the Big Crunch scenario, time may experience a dramatic reversal. As the universe collapses and everything converges on a singularity, the laws of physics as we know them break down. At the center of the Big Crunch, time and space may cease to have meaning. As space-time is compressed to an infinitesimal point, the concept of time might disappear altogether, ending with a return to the singularity where time began. The cyclical nature of this scenario implies that time does not have an end, but is part of an ongoing loop, a series of expansions and contractions that repeat endlessly. The Big Rip, on the other hand, presents a scenario where time's flow is violently interrupted by the tearing apart of space-time itself. As the universe accelerates toward its final rupture, the flow of time could be altered in unprecedented ways. The destruction of cosmic structures and the disintegration of particles could lead to a breakdown of causality, the foundation of time itself. If the universe is torn apart in a Big Rip, time may come to an end, or rather, time could become irrelevant in a universe where space and matter are no longer present in any meaningful way. Quantum mechanics and the ultimate fate of time. As we approach the ultimate fate of time, quantum mechanics enters the picture as a critical factor. While the classical understanding of time, as presented by Newtonian physics and general relativity, views time as a continuous linear progression, quantum mechanics introduces an entirely different perspective. In the quantum realm, time is not a fixed, absolute concept. Instead, it can be probabilistic, uncertain, and deeply intertwined with the nature of particles and the forces that govern them. One of the key challenges in understanding time's end is reconciling quantum mechanics with general relativity. General relativity governs the behavior of massive objects like stars and black holes, while quantum mechanics describes the behavior of particles at the smallest scales. These two theories work extraordinarily well within their respective domains, but they are fundamentally incompatible when it comes to describing extreme events, like those at the center of a black hole or the beginning of the universe. The quest for a theory of quantum gravity, a unified theory that combines the principles of both quantum mechanics and general relativity, remains one of the most important pursuits in modern physics. It is within this theory that we may find the key to understanding how time behaves in extreme conditions and how it will behave at the end of the universe. One potential resolution to the issue of time at the end of the universe comes from the concept of quantum fluctuations. According to some quantum theories, even in the emptiness of space, there are fluctuations that cause particles to spontaneously appear and disappear. These fluctuations suggest that space-time itself is not smooth and continuous, but rather discrete and subject to quantum processes. If time is not an absolute unchanging flow, but rather a dynamic, evolving entity, the end of time may be more complicated than we can imagine. The very nature of time may change as the universe approaches its final state, potentially leading to a breakdown of the laws of physics and the cessation of time altogether. The multiverse and the end of time. As we consider the end of time, it is also worth exploring the possibility of the multiverse, the idea that our universe is just one of many in an infinite collection of parallel universes. The multiverse theory suggests that there are countless other universes, each with its own set of physical laws and constants. These universes could be born from quantum fluctuations, or they could exist as separate bubbles within a larger cosmological structure. In this view, the end of time in our universe might not represent the ultimate end of everything. Instead, the death of one universe could simply be part of an eternal cycle of birth, death, and rebirth, where the multiverse continues to exist even as individual universes come to an end. The idea of the multiverse raises the possibility that the death of time in our universe is not final. As one universe dies, another may emerge, leading to an infinite series of cosmic cycles. While this concept remains speculative, it provides a framework for thinking about time in the universe that transcends our conventional understanding of an ultimate end. In the multiverse model, time does not end with the death of one universe. Rather, it continues on in other realms, and the fate of our universe may simply be one chapter in an ongoing cosmic story. What does it all mean for us? As we approach the final questions about the universe's end and the fate of time, we are reminded of our place in the cosmos. The universe, with all its vast complexity and beauty, will eventually come to an end, whether through the slow death of the Big Freeze, the explosive collapse of the Big Crunch, or the violent tearing apart of the Big Rip. But no matter how the universe ends, time will continue to be central to our understanding of existence. Time, as we experience it, may be finite, but its implications for our lives and our understanding of reality are far-reaching. As we explore the mysteries of the cosmos, we are reminded that time is not just a scientific concept. It is a fundamental part of our consciousness. The passage of time shapes our experiences, our memories, and our perceptions of reality. The end of time is not just a cosmic event. It is a concept that resonates deeply with us as sentient beings. It is a reminder of the impermanence of all things and the fleeting nature of existence. The ultimate fate of time and the universe remains uncertain, but as we continue to explore the cosmos, we will inevitably learn more about the forces that govern our universe and the nature of time itself. The death of time may not be the end of everything. Rather, it may be the beginning of a new understanding of the cosmos, one that transcends our limited perceptions of space, time, and existence.